Now we will start talking about what's generally called orbit theory. Okay, all of this, all of what we will be discussing in this module, in this part of the course, is available in a file called module 1B. I'll put it up on the site soon. Okay, so what does this deal with? It deals with the motion of charged particles in electric and magnetic fields. Okay, now, yeah, so we will come to this in a minute, but I just want to emphasize that this is really nothing new for you. Okay. You know that the force on a charged particle in an electric field is this. Well, we should write Q, all right? And you know that the force on a charged particle in a magnetic field is depending upon the system you're using. You'll either have a 1 over c or some kind of constant in front of it. So I'm not writing the constant. So I'm simply writing it as a constant proportionality, like that. Right? So an electric field just simply accelerates the particles. It depends only upon the charge. And a magnetic field does not accelerate particles, of course. Well, it does not increase the energy of the particles. It accelerates the particles, but the force is proportional. It only acts on moving particles, right? And the force depends upon the velocity. So this is the well-known Lorentz force. Right? So you know this. Okay. But this is important. But we thought that the whole point of we made a big deal about plasma as a collective. Yes, a plasma comprises of charged particles, comprises of many charged particles like this. But we made a big deal about the fact just now. I mean, just before this lecture ended, we talked about. Started just before this lecture. We were talking about Debye shielding, plasma oscillations, and things like this, which was all about collective effects. Okay, as opposed to test particle description. This is very much a test particle description, what we're going to talk about. Okay, now, yes, you would be right in thinking so, but then you see this is relevant for low density plasmas. For instance, some situations in fusion plasmas, things like the Earth's magnetosphere, the outer reaches of the solar corona / the solar wind, to name a few. Okay, so when the plasma is low density, and there's one other important thing, and I'll come to that. This kind of description is important. Okay, and you see, we are dealing with orbit theory. Deals with the dynamics of high energy particles in tenuous plasma. So it's not just tenuous plasmas, tenuous meaning low density, thin plasmas, but also when the particles that you're talking about are genuinely test particles. Okay, here's the plasma. Okay, lots and lots of charged particles, lots and lots of small charged particles. But what you're talking about here is not, I'm trying to see, yeah. So what you're talking about here is the dynamics of just a few high energy particles like this. Okay, these are the ones you're talking about. Okay, so these would be test particles, okay, in a tenuous background plasma. This is what we're talking about here. Okay, so the dynamics of these red particles. Okay, these are, and the reason I've drawn this with wiggly lines is that there are so many particles that you might as well, well, I was going to say you might as well adopt a fluid description, but if the plasma is very tenuous, then maybe this fluid description can still be a little iffy. So we will keep it at this. Okay, we will just say, what we will emphasize is the fact that the background plasma might well be tenuous, but the test particles are distinct. The test particles in some sense are even more tenuous. There's just a few test particles. There is no way you can call this collection of test particles a plasma. Follow? And how are these red particles different from the particles that make up the blue background? Well, these are, for instance, high energy particles. The temperature of the lower of the background plasma might be something, some T1. Okay, and we are talking about like that. Okay, maybe I should write this better. One is this is what I mean. Okay, so the red particles are very, very high energy, very, very high temperature. If you can ascribe a temperature to them, okay, it's better probably to think just in terms of energy. Okay, they are so energetic that they don't really belong to the background plasma. They are genuinely test particles. All right. Okay. So no, I don't. Yeah, right. Yeah, and orbit theory is relevant when the interaction of the particles, of these red particles that we talked about, with macroscopic external electromagnetic fields, okay, is more relevant than with the self-consistent fields associated with the individual, I should qualify this, individual background particles that comprise well, that's obvious. When I say background, it's the individual particles that comprise the background plasma. Okay, you see the microscopic self-consistent fields. What I mean by that is the background plasma, the particles comprising the background plasma are jiggling around, right? So they're generating by virtue of their motion. They are generating magnetic fields, right? And there might be a little bit of charge separation and so on and so forth. So they're also generating electric fields, but that is not so relevant for these test particles. What's relevant for these test particles is you have a background, okay, comprising relatively low energy particles, for instance, okay, and it's relatively thin, and so that's a relatively quote unquote low energy plasma, if you will, and you've got very high energy test particles, and they respond to externally imposed from somewhere else. Okay, someone else put in a magnetic field, someone else put in an electric field. From outside the, what should we say, from outside the domain in which you're considering. In a lab, it might be, the plasma is confined in a tokamak, and the magnetic field is generated externally by external coils. It's not due to the plasma itself or the electric field. In case of the Earth's magnetosphere, well, the Earth generates its magnetic field, and that's permeating the plasma. And the test particles are responding to the magnetic field thus generated. Okay, so it's very important to keep all these caveats. So this is what we will be talking about, but it's very important to keep all these caveats in mind before we go ahead, because yeah. So right. The rest will be, not very, when we start talking about this, the details might well be new for you, but the basics are not. Okay, you know about the motion of charged particles in electric and magnetic fields. This is something you're familiar with since, 12th grade. So, That is not so new to you. And we're not talking fancy relativistic effects. We're just talking basic, non-relative for the time being, just non-relativistic particles. So that's, pretty familiar. Right. So this is the outline of what we'll be talking about. We will be considering, progressively higher levels of complications. We'll begin with the simplest situation first: particle motion in electric and magnetic fields. We will, so electric and magnetic fields, fine, but are these fields uniform in space or non-uniform in space? In other words, is there a variation of is there a d over dx of B? Okay. So is there any non-uniformity? Okay. And is there a d over dt? Okay, that would mean by static and then time varying. So we will progressively consider these complications as we go along, and we will focus, especially, you can just jump into all the gory details, but it's important to focus, as with everything in physics. The key to making progress is to identify invariants, identify conserved quantities. So we will talk about one or two such invariants. They're not strictly invariant. They're what are called adiabatic invariants. We will talk about particle drifts. Particles are moving, but they also drift due to things like non-uniformity in the magnetic field, non-uniformity in density, and so on and so forth. And we will talk a little bit about applications to this. I definitely intend to do. This is not really my field, but I'll do what I can. And this is what we will be, chapter 2 of Boyd and Sanderson, and elements from chapter 3, 4, 5 of Starrock. Not all of it, obviously. The chapters 3, 4, 5 of Starrock is a lot of material. But what we will be doing, we will mostly be following Boyd and Sanderson here. Okay, but you will find so some of this material in that is also taken from these chapters of Starrock. All right. Okay, so let us now specialize to the simplest case. No electric fields for now. Motion in a static uniform B field. The static meaning no strictly zero. Okay. Uniform simply means any kind of d over dx of B is zero. There's no right. Okay, now when we write down the equations and everything, it's always useful to non-dimensionalize. Okay, it's always useful to look at how should I say, characteristic lengths and characteristic time scales. Okay, a natural length would be the particle gyro radius. You know that and this is why I also specified this in the what was that? In the prerequisite problem set that I gave you, problem set 0, right? Please derive this. This is something that you know how to do. Please derive the fact that in a magnetic field that's pointing out towards you, a charged particle will execute a strictly circular motion, and the radius is the Larmor radius. This is what. Okay, so this is a natural length to keep in mind, and the natural frequency would be the gyro frequency, the frequency at which it gyrates. Okay, that's, strictly speaking, is angular gyro frequency. Okay, often what happens is, this is the reason. The second point is the reason it's important to keep this in mind. Often, if you have L as some kind of a macroscopic length scale, the gyro radius is much smaller than the macroscopic length scale. And often, if you have a time scale T, the gyro frequency is much so 1 over T would be so 2 pi over T would be some kind of frequency, right? So what we're saying is that F over omega, right, is much smaller than 1 sometimes. Okay, so the frequencies that we're talking about are much, much faster than the gyro frequency. So on and so forth. Not always, okay, right. And if you can identify these kinds of ordering parameters, you can expand the motions perturbatively. We will see what this means. Some of you might already understand what this is saying. You might have come across perturbative expansions in other contexts. Right. Yeah. So what I mean by this is that we can think of averaging over, like we said in the beginning. Suppose consider like this. Consider a magnetic field that is like this. I mean, I know for now I said motion, we will be talking strictly about motion in a uniform B field, a B field that does not vary in space. But for now, bear with me. So let us consider a B field that looks like this. So how do you think, a charged particle, say an electron, would behave in this? An electron with some amount of parallel motion. Okay, so it executes a helix. Right, so it does this, right? Now, it would be intuitively obvious to you that if the RL, the gyro radius is much smaller than some kind of length scale, say this length scale, some length scale over which there is appreciable change in the direction of B, then we don't really need to focus on the gyro motion, or on the fact that the electron is gyrating. Okay, and what's more, if our time scales are large enough that if we're only looking at large time scales, so that the gyro frequency, this is very fast. So my camera shutter I'm taking long exposure photographs, suppose. Okay, in which case I don't really need to worry about this gyro motion. I can simply worry about what's called the guiding center, the center of this motion, the center of this gyration, and the center of the gyration just follows the magnetic field, like that. Okay, this is what's called the guiding center. This is intuitively it makes sense. When you write it down mathematically, it's important to keep all the algebra disentangled in your mind and understand what you're doing, obviously. But this is what we will be, shall we say, aiming towards. Okay, this is intuitively it makes sense. Yeah, and we will talk a little bit about the concept of adiabatic constants of motion. We will, yeah. So let's skip over this for the moment. Yeah. So what are we neglecting? We are neglecting any kind of radiation. A charged particle orbiting in a magnetic field is accelerated. It's another matter that its energy doesn't change, but it's accelerated. So you expect it from classical electrodynamics. You know that an accelerated particle emits radiation, right? So we neglect that. Okay, we neglect the fact that the particle emits radiation and therefore it slows down. This is another way of saying that the external fields are dominant. The self-consistent fields generated by the motion of the particles are neglected. All right, and this is the kind of picture that that we will adopt. Simple. So say the magnetic field is pointing in the z direction. For without loss of generality, you can always add other directions to it, and say you have a center of gyration x naught y naught, and so you have a perpendicular velocity and a parallel velocity. The parallel velocity is not affected by the magnetic field at all, and so yeah, and in this case, this is a positive charge just gyrating. Okay, and This is the usual, you know. I mean, this is the electric field. I mean, so soon we will say that the electric field is 0, and so this would be the Lorentz force. Right? So this would be the F, and this is MA. F equals MA. That's all you're writing down. You specialize to a constant B like this, yeah, and you say that I neglect electric fields for the time being, and I quickly figure out if you expand, I mean, if you write this down in all its coordinates, you disentangle the coordinates, and there's only a z component of B, you will immediately find out that there is no acceleration in the z direction. Z double dot, so z double dot is simply this. Okay, similarly this is simply d square over dt square of r of j. In this case, it's a full vector. We're simply talking about the z direction now. Okay, so also the d square x dt square is omega times dy dt. D square y dt square is minus omega times dx dt, where the omega is the, this is the gyro frequency. Okay, also, and the MA dot V, this is dr dt is V. So MA dot V is 0. In other words, what this is saying is that the perpendicular and parallel kinetic energies are conserved. No surprise here, because magnetic fields do no work. All right.